Aachen, and it is my pleasure to moderate this session. The focus of this session is on anomaly detection and clustering, and we will have three fascinating speakers. Each speaker will present his work in 50 minutes, and there will be 5 minutes for discussions afterward. Please feel free to write your questions in the Q&A section or use the raise hand option via Zoom. So let's start. First, I would like to ask Gabriel Marquez Tavares to present the first presentation that is a joint work by the University of Milan, Londrina State University, and Khalifa University. Gabriel is a PhD student at the University of Milan, and his main research is on anomaly detection, trace encoding, and more generally on online process mining. Okay, Gabriel, floor is yours.
Okay, thank you very much for this great introduction. I also thank all the attendees who are here for my talk, and I'll present to you now the work on anomaly detection on event logs with a scarcity of labels. And this is a joint work where my contributors are Silvio Barbon, Paulo Tiravolo, Ernesto Damiani, Nicolas Omori, and myself. So to start with, I want to give you a general overview of the process mining area, which I'm sure most of you are very aware of. We have the information systems which control and record the execution of activities within a business process. In these activities, executions are recorded along with their times, their resources, users, and so on, depending on the business process. And all these recordings go into an event log. And here in the, starting from the event log is where all the process mining magic begins. So I have listed here the three main traditional tasks of process mining, which are process discovery, conformance checking, and process enhancement. But of course, we have several additional tasks such as process prediction, variant analysis, anomaly detection, and so on. So why am I showing this overview of process mining? Mainly because I want to highlight two very interesting aspects which are important for our work here. So as you can see, in process mining, we deal with a lot of event log data in several layers and different also artifacts. So we have the event log, we have cases and events, but we also have process models and so on. So it is necessary, it is required that we have good quality encoding techniques to transform and to compare and to provide common grounds for the execution of procedures, analysis, and algorithms. So the encoding techniques are a necessity in process mining scenarios. And the second thing I want to highlight to you is that traditional process conformance checking is usually the main task used for anomaly detection or deviant detection, and it's based on the comparison of the event log and the process model. And our work is also on the same area, but using different perspectives. So as I said, our work is based on a scarcity of label scenario, and the traditional conformance checking is always relying on the comparison of the event log and the process model. But this raises a problem that it's always depending on a good representative model. So we know that conformance checking techniques are very precise, mainly alignments, but by relying on representative models, this could be a problem since we know that in reality, many times good models are not available. So to overcome this issue, machine learning techniques have been more and more employed in process mining for anomaly detection as an alternative to process-aware methods. Mostly because machine learning techniques do not need a process model to compare with the event log. And we have seen that supervised machine learning has been used a lot in this scenario. But on the other hand, supervised machine learning also requires an abundance of examples, such as normal examples of traces and also anomalous examples and several anomalous examples. And this also raises a second problem because in many scenarios, you don't have labels for anomalies or even normal traces. And we know that manual labeling is costly for the organization because someone needs to be there spending time and resources labeling. But there's an even deeper problem, which is the labeling of unknown traces or unknown anomalies. And this can be an additional problem for labeling. So given the scenarios in both of these problems, in our work here, we are proposing a method based on one-class classification algorithms that overcomes both of these previous issues, because one-class classification algorithms do not need process models to compute to detect these anomalies, and also the behavior is learned based only on normal examples. So we don't need anomalous examples, or we don't need labels for anomalous traces to detect anomalies. But of course, the one-class classifications algorithms by themselves are not enough. We do need also a self-supervised encoding technique in order to provide good encoding vectors or descriptors of our traces. And as we don't have labels, we need a self-supervised encoding technique. So also we have seen that in recent works, word embeddings have been used a lot in process mining. They are based on natural language processing, and mostly because activities do describe in several scenarios an action being performed, and then we can aggregate these activities and form some kinds of sentences representing the trace. So these encoding techniques based on word embeddings provide these common grounds for analysis, and the activities represent these actions being performed. In our work here, we have used the word-to-vec encoding technique, which is very well known in the natural language processing area literature. And the word-to-vec is a two-layer neural network created to reconstruct the linguistic context of words in a corpus. And this means that words appearing in a similar context will generate similar encodings because of the context surrounding these activities. And in our work, we understand traces and activities as sentences and words respectively. So overall, our method is based on a self-supervised technique, word-to-vec, and in conjunction with one-class classification algorithms to detect anomalies in business processes. Now going a little bit in details in our experiments, we have tested a wide set of event logs, both synthetic event logs and real life event logs. And these event logs are based on other works which have also used these event logs, and they are very well known also in the anomaly detection. And now I'll explain to you very quickly these anomalies we have been exploring. So we have the normal trace and then 6 types of anomaly. The first one is inject anomaly, when one activity is injected in the control flow perspective, and this activity is an activity out of the vocabulary of the process. Then we have the early anomaly, when one activity is executed too early in the trace before it was supposed to be executed. Then we have the rework anomaly, where one activity execution is doubled because this activity happens more than once. Then we have the late anomaly, when one activity is executed too late in the trace, and the skip anomaly, where one activity is skipped, so it's missing the final trace. All these anomalies affect the control flow perspective of the trace. And finally, we have the attribute anomaly, which affects the data flow perspective because it affects the attributes related to these activities. And the goals of our experiments are threefold. So we want to evaluate the word-to-vec encoding capabilities. Also, we want to compare supervised machine learning and one-class classification methods for this classification test, which is the identification of anomalies. And finally, we want to evaluate the impact of these different anomalies in the event log. For these experiments, we have tested several vector and window sizes for word-to-vec. And also, we have applied the SVM representing the supervised machine learning technique, and one-class SVM and LOF representing one-class classification algorithms. And let me know that we also have performed the hyperparameter tuning in order to obtain the best results out of all these 3 algorithms. Now diving into our results, first we'll evaluate the word-to-vec descriptive performance. On the left-hand side, you can see the variance of the word-to-vec vector size, and on the right-hand side, you can see the word-to-vec variance on the window size from the values I have shown you before. And we can see a very stable results across these different variations of vector and window sizes. And all the algorithms being using for the classification maintain their performance over all these across these different hyperparameters configurations. This means that word2vec is very robust into using different hyperparameters, and overall represents very well the trace as an encoding technique. And we can say that lower values of vectors and window size are faster to be computed than higher vectors. As a next evaluation, we have the overall performance and also the anomaly impact. And on the left-hand side, you can see the overall performance of the three algorithms we have tested. And it's clearly from the F-score perspective that the LOF outperforms the other methods. Then we have SVM and one-class SVM. So this box plot shows us that one-class classification not only can be a solution in a scarcity of label scenario, but also outperforms traditional machine learning techniques, which have been used in several works for the detection of anomalies in business processes. And even if you consider one-class SVM, which has a lower F-score than SVM, it's still an interesting technique to be explored in the consideration if you consider a scarcity of label scenario. On the right-hand side, you can see the impacts of the different anomaly types we have used here. And we can say there are three main groups of anomalies which we can perceive here. So the first group is the insert, rework, and skip anomalies, where both LOF and SVM obtain the highest performance in the F-score. And these anomalies, we can say they are easier to be detected and encoded by word2vec because they have a higher impact on the control flow perspective. For example, if you select insert, where a random activity out of the process vocabulary is inserted in the control flow perspective, the rework activity where the activity is reworked, like looped. So this has a high impact in the control flow, and it's easily encoded by, captured by the word2vec encoding algorithm, and consequently also easily detected by the classification algorithms. As a second group of anomalies, we can see early and late anomalies where the SVM performance decays a little, but LOF still maintains a high detection quality. And this is mainly because the early and late anomalies are a little bit harder to be detected. Not that they are not anomalies, but they affect the control flow more subtly. So the activities are still being executed, though in the wrong order. So they are still in the trace composition, but they are subtle because there's just a change in the position. And then finally, the third group is the attribute anomaly, which impacts the data flow perspective, and it's the hardest one to be detected, both by the encoding and, of course, by the classification techniques later. From the execution time comparison, we have seen good performance over all the three algorithms, though SVM has across all the event logs has the lower time consumption when compared to the other techniques. But we see that the window size and the vector size for the word2vec impacts a lot on the time consumption. So this must be considered in an application. Then, considering the hyperparameter selection, we have done hyperparameter tuning. And as is very well known in the machine learning literature, SVM is an algorithm which is harder to be tuned. As you can see in the sigmoid kernel, the best performing setup is very close to the worst performing setup with only a change in the C hyperparameter. So it's difficult to tune SVM, while on the other hand, one-class SVM is very easy tuned, and also LOF generally is easy to tune because lower values of number of neighbors and contaminations leverage higher quality in F-scores values. So overall, we can say that one-class classification techniques are a good solution for a scarcity of label scenario and may reach even higher scores than traditional supervised machine learning techniques, and making it viable in a scarcity of label scenario only where only normal examples of trace executions are available. SVM has a higher time a better time performance, but on the other hand, also depends a lot of in hyperparameter tuning. So this can be a problem in a real application when using SVM. We can also say that Word2Vec is very robust and stable across all the different hyperparameters we have used, and that also anomalies have a different impact, different anomalies impact differently in the event log quality encoding. So in this work, we proposed a two-step solution for anomaly detection, which is the self-supervised method based on word embeddings to encode trace behavior, and in conjunction with one-class classification algorithms for the detection of anomalies in business processes. For future work, we consider adding multiple perspectives, explore other aggregation techniques, and apply also one-class classification in online process mining. Thank you for your attention. If you want to contact me for further discussion, here's my email, but also feel free to have any question here. I'll happily answer you. Thank you.
Thanks for your presentation, Gabriel. You have achieved very good results. Let's see if there is any question in the chat box. Okay, I couldn't see any question yet. So to warm up, I will ask the question, the first question. So sometimes it is very difficult to, and sometimes very challenging to distinguish somehow between noise or infrequent behavior with normal, with anomaly behavior somehow. So we have very infrequent behavior, noise, and anomaly behaviors. Would you please share your ideas about how can we distinguish these two different behaviors using your approach?
Yes. Our assumption here in some of our findings highlight that even though infrequent behavior could be considered an anomaly, Word2Vec encoding can, in most cases, still capture this infrequent behavior as a normal behavior, if it's a normal behavior, mostly because of the context of the words or the activities which are considered in the encoding algorithm. So when we extract the encodings. So even though infrequent behavior is can also sometimes be confused as an anomaly, overall Word2Vec indirectly understands these different execution traces, even though it doesn't have a process model to compare the traces with.
Thank you very much. If I have a chance to ask another question, I'm wondering how can you position your proposed method with some techniques like clustering, because we can also use clustering that there is no need to be trained. So how you position your work with that approach?
Yes, that's a very nice question. Thank you. So clustering is also an interesting solution in many cases, but still, in most cases, even a process expert or someone, a stakeholder, can name a few traces which could be normal traces. So given that, generally, with one-class classification techniques, you can still have high performance. Where in clustering, you can still can detect different variants, let's say, but you may not have these labels. So if you only have a set of few normal traces, you can apply these one-class classifications and obtain nice results for anomaly detection.
Okay, thank you very much, Gabriel. My last question, if there is no other question from the audience, would be about, there is a question.
Okay.
Let me see. Esther, do you, Esther, sorry if I don't pronounce your name correctly. Do you want to ask your question by yourself? So you should just unmute. So I will read the question. So he's also working on anomaly detection, and he's interested to know if you have any heuristic to choose the threshold, because choosing the threshold could really affect on the, for example, if you use probabilistic method, it's really affect on the number of false positives. What do you think?
Yes, thank you for your question. It's an interesting point. But in this method we are proposing, there are actually no heuristics in the sense of choosing a threshold, because our encoding method is a self-supervised encoding method. So it's only based on the traces, and from these traces, the Wordvec can produce these encoding vectors, which will later be used as a one-class classification. I could say that in the sense of tuning, we do not need to propose or to play with thresholds, but we do have to tune the hyperparameters of the classification. So it's a different tuning problem, but it's not it's still somehow related. But just to be clear, we do not play with these thresholds because we're not starting from a probabilistic standpoint.
Thank you very much, Gabriel.
Thank you, my pleasure.
Thanks again for your presentation. Let me move to the next presentation that is also about anomaly detection. The second work will be presented by Ludwig Zellner, who is doing research in the Ludwig Maximilian University of Munich. Also, I want to ask Ludwig to kindly share your screen with us. Ludwig will present the trace ordering for anomaly detection paper. Go ahead.
Yes, thank you very much for that nice introduction. Can you see my slides?
Yes, we do.
Perfectly. Thanks for having me at the ICPM 2020. And my talk will be about trace ordering for anomaly detection, which is called TOAD for short. And so let's dive right into it. At first, to understand the goal of this paper, we have to clarify some types of anomalies and which of them we have in mind to detect. So true to the name of the paper, let's talk about toads. Let's assume we have some data gathered from pools or lakes nearby, and we look at the toad population at those lakes. We expect somehow to see a low but constant number of toads over the year. So you see a plot with the months of the year, and on the y-axis the toad population at some spawning waters. But here we suddenly see a peak in the data. So we explain it because the period of increasing number of toads fits well, that this peak is due to toad migration in spring. And this would correspond to a point anomaly. And we start to plot another year of toad population, and we get the result, which you can see on the right-hand side. So far, we learned that the peak in February and March corresponds to toad migration. But the plateau in the data around May and June is new to us. So we try to explain it, and we learn that this fast decrease in April and a small increase in May and June could correspond to late frost, which means that some toads are somewhat late to get to their spawning waters. And this can be seen as a contextual anomaly, since the first peak occurs in the context of expected toad migration, but the second smaller peak is new to us. And last but not least, let's look at 4 successive years of toad migration data. We can see every year there are the expected peaks in spring, which we learned. But in year 3, it shows a different behavior because there are not that many toads as the other years. So possibly a new road was built between the toads and their spawning waters, which keeps the toads from returning back. So if we assume that multiple spawning waters show the same effect in the data, this can be seen as a collective anomaly, because a set of related data is anomalous with respect to the rest of the data. And this is exactly the type of anomaly we want to detect in the process data. And for our approach now, we are concentrating only on the time perspective of the data for now. So to fully understand the approach, we need some preliminary knowledge, which is related to the field of density-based clustering. And here we have popular algorithms like dbScan or optics, which analyze points with respect to the density between them. And dense regions in the data thereby get separated by regions which are not densely populated. And we use optics for our approach, and for that we have to know these important terms which are following. At first we have the min points parameter, which is the number of points which are required to form a cluster. And then we need to know the core distance. And you can see in the graphic on the bottom right side that this is the smallest distance to the point which is required to fulfill the min points condition. And we need the reachability distance, which is the maximum of the core distance of a point and the actual distance between 2 points. And this means in the illustration that for point O, the reachability distance is given by the green arrow. And the epsilon value is only required to restrict the maximum distance of each point to be considered and thus speed up the algorithm. So to further illustrate the algorithm, you can see some points here in two-dimensional space, which are analyzed regarding the density, and then they are plotted in a reachability plot. So the steps of the algorithm are first to decide for the reachability distance for each unprocessed point by taking the maximum of the core distance and the actual distance between 2 points. And then we use a priority queue to process each point by its reachability distance. And therefore, the result is a plot with the data points on the x-axis and the reachability distance on the y-axis, which you can see on the bottom of the slide. And this leads to different troughs in the reachability plot. And here, for example, we have possibly 3 clusters. A green one, a blue one, and a yellow one. And the green one forms the trough on the left-hand side. And we can localize the blue cluster on the right-hand side. And additionally, there is a yellow cluster inside the blue one, which has somewhat a higher density. So there is a trough inside the trough of the blue cluster. So we can say the denser the clusters in the data, the deeper the troughs in the reachability plot. So it is very important to know that in this approach, we focus on temporal deviations. And for this, we use temporal deviation signatures, which are explained on this and the next slides. So to find the anomalies, we adapt the idea of standardization by set scoring. And this gives us a suitable representation of the deviations we aim to find. So here you can see a toy example on the left-hand side with 5 different cases, C1 to C5. And at first we compute the set of relation durations between each event pair. This is represented for case 1 by the arrows. And then we derive the mean and standard deviations. And you can see the relation, the computed relation duration, the mean and the standard deviation in the matrices on the right-hand side. So next, we perform set scoring, which deals with unstable activities by downweighting them in comparison to activities with small standard deviations. So with set scoring, we have the advantage to align short-term and long-term activities in the same model. So we can compute the temporal deviation signature for each case, which is a matrix with the standardized activity relation, but only given the relation is present in the case. If that's not the case, then otherwise 0 is assigned, which you also can see in the matrices and the temporal deviation signatures on the right-hand side. So as you can see, we have here the temporal deviation signatures for case 1 and case 4. And the cases which drive this approach possess deviation scores next to 0. So for example, in case 4, so in the matrix on the lower right, the duration between A and C seems typical, because we have 4 out of 5 cases which have similar durations between A and C. And the deviations are shown in yellow and blue in the deviation signatures. So for example, in case 4, the relation between A and B says that relatively speaking, the activity B is somewhat delayed, which also reflects in the temporal deviation signatures. So in the next step, we treat the temporal deviation signatures as vectors. With the vector representation, we can use the signatures to compute distances between them. And for our approach, we use the Euclidean distance, but other distance measures are also possible. We then expect cases which do not hold deviations to be represented as points around the origin. And as explained before, we can now run optics on our dataset and get a corresponding two-dimensional reachability plot, which shows the traces ordered by their reachability distance, which means that the successor of each data point is the point with the smallest reachability distance out of the unprocessed points. So the reachability distance of the traces are shown in blue in the plot on the right-hand side. As you already could see, there is another line plotted above the reachability distances. To actually detect anomalies, we have to filter out negative peaks, which indicate deviating cases which are denser than others. And this is done by applying a filter. Here we use the Swidzky-Golay filter as a baseline and calculating the difference between each reachability distance of a case to this baseline. And depending on this difference, we can decide if there's a collective anomaly or not. And we use this filter because it can cope with the high reachability distance at the border of our plots. Now we are getting to the experimental setup with which we evaluated our approach. For the optics part, one parameter is required. It's the min points, which controls the granularity of our two-dimensional reachability plot. And for the filter part, we need the window size, which says how many points are going to be considered, and the polynomial degree, which is the order of polynomial which will be fit to these points in the regression step. And for the automated peak finding, we have to specify the width and the prominence of a peak, which means the maximum difference between the reachability distance and our baseline. And we use the BPIA challenge datasets from 2015 and 2017. Where for the former, we added a delay, which we had to correctly identify between the realistic noise of the original datasets, and for the latter, we identified a subset of cases which differs in its temporal execution as a ground truth, which we then wanted to detect as a classification problem. So let us first take a look at the fitness and precision scores for the BPIC 2017. Here we compare these values against the min points parameter. The blue line contains all original cases, and the orange line cases with a minimum length of 5, and the green one only accepted offers. So we recognize a drop in both precision and fitness at min points equals 40, since small anomalies vanish when choosing min points greater than the size of the anomaly. So we have to choose min points significantly smaller than our expected anomaly size. Furthermore, the fitness drops slightly over the min points values. That is due to the smoother reachability curve when the number of min points increases and the traces at the borders of the values are not detected. So regarding precision, we can see a clear drop around min points equals 20, which can be explained by a higher number of short cases, which naturally have smaller distances. Furthermore, they are anomalous by size, hence they are detected first most of the time. Another important aspect gets clear if we look at the modified event log of BPIC 2015. Here we injected anomalous traces by delaying one event by a certain number of hours. As we can see by the numbers in the upper left, the fitness values are not that good, but we get maximum precision. And this shows that the fitness value is not necessarily of the same importance as the precision value, since our approach is designed to find collective anomalies, but to neglect false positives. I mean, spending resources on chasing false anomalies should be generally avoided. So Toad qualifies as a starting point from which the borders around the dense cores have to be investigated. And we derive this, for example, from the plot in the lower half, where some undetected anomalous traces are marked by orange crosses. So for the last part, we come to the future work. One of the limitations of our approach is the overloaded zero as a deviation score. So on the one hand, it could be that there's a non-existing relation between activities, and on the other hand, the relation exists, but there is no deviation. And as I already said, there are many other distance metrics which could be used here, which we plan to further investigate. Furthermore, the application on event streams has great potential, and our approach could also be extended to other attributes besides the time perspective. So to sum up, with our approach, we are able to first detect clusters which have collective anomaly characteristics. And by this detection, we can improve the overall process. The parameter min points should be chosen carefully because of sensitivity reasons, and narrowing the search space is definitely beneficial for our approach. And one thing I did not mention so far, from the optics plot, we can derive the subprocess which visualizes the anomaly as a process model. So you can see here on the right-hand side that the process model on the lower half is a valid submodel of the process model in the upper left. So that concludes my presentation. Thank you very much for your attention, and especially for attending the last session of this great conference. And I'm very happy to answer some of your questions.
Thanks a lot, Ludwig. Let's see if there are some questions by the audience. There's one question. So, Pavlos, feel free to ask your question.
Thank you, Ludwig, for the presentation. Very interesting topic. Could you please tell us how you could you please share some experience of your experiments? I mean, why a density-based algorithm is better than a distance-based algorithm or a graph-based clustering algorithm? And if I may probe on that, you use a distance. You calculated the distance between two vectors, and you are not considering the ordering of activities, if I'm right. So, did you observe any traces that were similar, maybe due to some compensation of this aggregation approach, despite the fact that the ordering of the trace was different?
So thank you for the question. That's actually a valid point. So I would not generally say that density-based clustering is better than other clustering approaches. But here we, for example, if we look at the workflow, then we would not detect the anomalies. So what we do here is combining the time perspective with the density-based approach. Because, for example, on the last slide, which you can see here, this causal net is a valid sub-model of the causal net of the BPIC 2017, which you can see on the upper left. And so we would not detect the anomaly by the workflow itself. So it's beneficial for us to combine the time perspective with the density-based approach, and so we can detect anomalies at least in the time attribute. And could you please repeat the second question of yours?
Yes, of course. You don't consider the order of the activities, if I'm right. You just consider the temporal deviations. So when you calculate the distance of the two vectors, is it possible to have two vectors, two traces that do not have the same order of activities, but they appear at a close distance because of some kind of compensation of some kind of, I don't know. So, I mean, maybe one activity is very distant in time, but all the other activities are very close, but that particular activity that is distant happens in a totally different position. Have you observed empirically this?
So actually we are creating our vectors by using the relations between every activity. So the relation duration between every activity. So if there is no relation duration, we only set a 0 as a value at this point. So I think therefore it cannot be that the vectors are somewhat similar, but the problem is that if we don't have relation durations between two activities, this could be confused with a similar vector. So this way round, this could pose a problem, yes.
Thanks for your answer. The next question will be asked by Will. Will, please go ahead.
Yeah, so thank you, Ludwig, for the presentation. Like I actually had a bit of a similar question to the second question of the person that just asked the questions. So for example, I can make it more specific. Like if I would have loops, how would you then count the duration? Because your example, you have the ABC example, and there it seems to be assumed that it's indeed happening ABC in that order. That it was not so clear.
So the thing with loops, I'm not really sure if we how we compute this. So
because if I have A, BC, 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 D, then yeah, you have many different distances between A and B and A and C.
So
if you see what I mean, right?
yeah.
Then you probably take the first one, but you're missing quite some information.
So intuitively, I don't know the answer to this question. So maybe I could look it up and write you the answer by email.
Yeah. So another question, but the question I just asked was very similar to the previous question. Another question I had was related to when we are doing, for example, looking at effects of, I don't, workload on how quickly people work and stuff like that. A big problem is always that in event logs, you typically see working days. So you can see somebody finishes it 5 minutes before 6 and then goes home, or the person doesn't finish it and then it's, I don't know, if it's on Friday afternoon, it will only be done on Monday morning, if you see what I mean.
Okay, so there's a break between or there's a relation which does not reflect the realistic duration. There's a duration which
so time gaps may be in absolute time, they may be very far apart, And if you look at the actual working hours of people, they are not far apart at all, although in an absolute sense, there is a gap of 2 days.
That's an absolute valid point. I think combining the time perspective with the workflow or with other attributes, it would help to compute better results in that cases.
Yeah. So thanks a lot for this nice discussion. For the sake of time, we should move to the next presentation. The last presentation will be presented by Farizand Karimi, who is a PhD student at the Chair of Enterprise System of Mannheim University. In this work, that is a collaboration of Mannheim University and Amir Kabir University, the goal is to provide a generic framework of trace clustering in process mining. So Farid, please go ahead.
Thank you very much, Mohammad Reza, for the nice introduction. I hope you see my screen.
Yes, we do.
Perfect. So hello, everybody. This is Farizand Karimi, and together with my co-authors, Jana Reza, Puya Sudmant, and Hartmut Höhle, we conducted this study, a generic framework for trace clustering in process mining, that I'm going to present in this session. Process discovery is the most popular component of process mining applications. Enhancing process models is still a critical challenge for process mining researchers. Pre-discovery activities such as noise reduction and outlier removal are applied on event logs so that the resulting process models are more beneficial. When it comes to flexible environments such as hospitals, that the process is naturally complex and it allows for significantly different variables, the idea of modeling the whole event log leads to a complex and ambiguous process model, which does not provide any valuable insights to the users. Trace clustering aims to cluster the so-called sub-processes to avoid mixing apple processes with orange processes. Over the past 15 years, researchers proposed various approaches for trace clustering in process discovery. The developed approaches vary greatly with regard to algorithmic capabilities, data characteristic, computational complexity, and integration of additional information. However, there is no generic guideline on, or let's say a big picture of trace clustering projects available to help researchers and practitioners to easily understand different corners of the a priori findings in this process mining niche. In our research, we face the same problem. So we decided actually to solve the solution first, and of course, share it with the community. In order to do so, we conducted a systematic literature review, looking for terms such as trace clustering and process mining together. We were surprised by the number of publications, 103 peer-reviewed papers, which were published between 2014 and 2020. 2004 and 2020, sorry. Our initial goal was to provide researchers and practitioners with a guideline to choose the right trace clustering technique for their purpose and to allow for the systematic identification of research gaps. So let's start with the finished model first. In the next slide, we will discuss the blocks in detail. But as you can see, this framework has three main gray areas in the background. Depending on the characteristics of the event log, the availability of domain expertise, and the computational resources or requirements of the project, these areas can be added or removed. Not the fundamental one, but the other two. Rounded boxes are on the very right, on the very left side of the model. Are entities, specifically the event log, which is either a basic one, which we will discuss it later, or an extended one. The normal boxes represent a major step or set of actions in a given trace clustering project. If boxes are drawn with double-lined effect, this means integrating domain expertise is possible in this step. Solid arrows represent the order of the or the flow of the steps, and dotted ones represent the metadata signals exchanged between different blocks or simply boxes. An event log can be a basic one. It means it contains only case identifier, events, and the order of events. Or it might have other complex context-related perspectives. For example, cost, user, duration, you name it. Data attributes in the event log are related to cases. We call them trace level data, or it can be related to events. We call them event related. We will later build features based on these attributes. A feature can be any property or attribute contained in the event log. As the overall goal is to assess similarity between individual traces, features are will be generated at trace or event level. Two data structures are typically used for feature generation. We categorize them as linear structure and nonlinear structure. Linear structure typically refers to simple data structures, such as scalars or arrays. Nonlinear structure, for example, graph and trace structures, are used when the nonlinearity behavior of traces cannot be fully captured by those linear data structures. Depending on the required features, numeric data or categoric data from the event log may get transformed from one type to another. Instead of working with the whole trace, one can process a subset of the trace, which is called an n-gram. Determining the length of n-gram is also discussed in detail in the paper. The generated features of the previous step provide the input for transformation. Feature transformation includes generating secondary features and assuring features quality and interpretability by applying techniques for normalization, collinearity, and dimensionality. Normalization ensures the comparability of features. Collinearity checks for redundancy, that is, eliminating identical or similar features. Dimensionality ensures a certain degree of richness. So multiple versions of one attribute exist in the final pool of features. So if feature selection removes, for example, a certain attribute, not all information is lost. In the last step of the pre-clustering phase, the generated and transformed features are reduced by feature selection techniques. Those techniques are needed to avoid problems with overfitting, precision issues, and extra processing costs, which can appear when using too many features. Feature selection can happen either in all at once fashion, we call it single view, or incremental fashion, we call it multiple view. The all at once approach usually yields relatively fewer features, whereas the incremental approach allows for selecting more features in the final set. Feature selection also allows to integrate domain knowledge to improve the selection process. Dealing with large event logs can be computationally expensive and time-consuming. Processing the whole event log, however, does not guarantee optimal results. Therefore, depending on the situation, it might make sense to pre-process the event log by splitting it prior to clustering. Principal approaches in dealing with large event logs can be labeled as parallel and evolutionary. In both approaches, the event log is split into multiple sublogs. The parallel approach exploits clustering and classification techniques to process all sublogs simultaneously. Processing each sublog yields a set of subclusters, which are merged to obtain the final clusters. In the evolutionary approach, randomly sampled sublogs are processed sequentially until either all sublogs are processed or the updated clusters do not change significantly. As far as we are informed, event log splitting approach is not implemented in the literature, but we included it in the framework because it's an established technique in data mining, which we propose to and recommend for future research, especially when dealing with very large event logs. Distance measure are a popular technique for measuring trace similarity. There are multiple ways to calculate the distance between two traces or their respective features, which vary according to distance type, granularity, and robustness function. Using them, we can compute a so-called similarity matrix, which contains pairwise similarity values for all traces in a log and serves as input for some clustering algorithms. We discuss it further in the paper. Second potential input for clustering algorithms are probabilistic models. For example, Markovian probabilistic models, which basically the probability of observing a trace given a Markovian probabilistic model determines to which cluster each trace belongs. The third option in clustering inputs is segment-based computation techniques. In this approach, using the computed features, a conceptual grid is built. The algorithm merges or splits the grid based on the similarity of the neighbors. It stops merging or splitting the segments when the model is satisfying. We considered three main approaches for clustering, namely full clustering, full classification, and partial clustering. In the full clustering approach, detecting the initial clusters, which we call them implicit class definition, as well as assigning all traces to those clusters, are all done by mainly by the clustering algorithm. This approach also allows for integrating experts' knowledge when defining the initial clusters. In the full classification approach, expert knowledge in the form of human grouping or to-be process model like documents is used to define the initial classes. We call them explicit classes that are later used by classification techniques to assign the rest of the traces to the clusters. In the partial clustering approach, a combination of clustering and classification techniques are used. Clustering techniques with the possible help of expert knowledge are applied to build the initial clusters based on limited part of the event log. Eventually, classification part takes the final cluster as its initial classes and continues with processing the rest of the event log. Well, usually classification and clustering algorithms, they have their own built-in objectives. That's, the performance, for example, measures that are reported. But we can also define specific measures for trace clustering. For example, if you are doing trace clustering for model discovery, then fitness or simplicity would be those extra evaluation objectives. These objectives are either sent as in an iterative fashion or as a one-time. We call it internal. When it's sent.
Farid, sorry to interrupt. You have only 1 minute.
All right. So internal feedback is generated for each iteration, while external is generated only once. So now I'm coming to the conclusion. For practitioners and researchers, we claim that we have a contribution. For practitioners, we want to give an overview over the current state of the art in trace clustering and take a first step towards building the big picture of trace clustering techniques and implementing approaches. Categories like extended data availability and extended process availability may help in this regard. The framework, however, in its current form lacks practical utility because it focuses more on the generic trace clustering process than on the capability of individual approaches. For researchers, we want to make it easier to position their own research with regard to the state of the art in trace clustering. There are no works on the clusterability, if I may call it, of an event log. That is the attributes that an event log has to fulfill for trace clustering to be useful. Depending on the characteristics of the log, some clustering approaches could be more useful than others. Now I'm coming to the conclusion. Sorry that I talk too much. There are too much content here in this paper, and we would like to cover the highlights at least in the presentation. Thanks for your attention.
Thanks for your presentation, Farid. There are several questions. So the first question will be asked by Anahita. Anahita, feel free to unmute and ask your question. We couldn't hear you, Anahita. So I will ask Paulo to ask his question. Paulo, please go ahead.
Okay, so now I think you can hear me.
Yes?
Yes.
Okay, thank you, Farid, for this presentation. I'm wondering if in thinking in the future, you will be able to predict model quality like fitness and precision simplicity based on the parameterization of a clustering algorithm. So I mean, based on how you select and you parameterize your clustering, if you can predict the impact that this will have on the quality of a discovered model.
So yeah, if I understood your question correctly, you're talking about the challenges in the quality or the measures for. I couldn't really hear your last part of your question.
I'm sorry. I mean, if you think that it will be possible to predict the quality of a model that is discovered observing and learning from a cluster using the parameters that was used in order to design the clustering algorithm.
Yes, this is correct. Evaluation is a big problem. And based on the typical evaluation metrics, as I said, that we have the built-in ones, that they are like the built-in metrics for evaluating the quality of the findings or the quality of the clustering models. You can also define those on top of them, but still this is challenging, I agree. And in the future, this should be, for example, enhanced by bringing the concepts from different disciplines. We also mentioned them in the paper, but this is a challenge that which has not been actually researched well.
Thank you.
Thanks.
So,
Anahita, can you ask your question? Because we couldn't hear you. So if you couldn't ask your question, I will ask a question about clustering. We see many times there is no limitation on the number of clusters. So for example, suppose that we have n variants in the event log, and we could generate n clusters and with perfect fitness and perfect precision. So what do you think? How can we put limitation on the on the number of clusters that we have? Because by increasing the number of clusters, we will have more process models, and analyzing all process models could be also complex for human.
it again depends on the approach. That's a valid question. Also, having dominant variants is a big problem, because then you lose the less frequent ones, and you have only 1 or 2 variants as the clusters. And having multiple, like too many clusters, also is a big problem. Using segmentation and those bottom-up approaches can handle this. But all in all, as we also mentioned, this is important that before applying trace clustering, because it might take a lot of process capabilities, before applying it, we check for trace clusterability. So we need to define those measures. And more and more measures are coming out. We are looking into those measures, which are mostly about event log quality or simplicity. But for trace clustering, maybe we need some new measures which we can decide whether we should apply trace clustering or not, and if we should, with which parameters.
Thank you. Will, please ask your question.
Yeah, so thanks for the presentation. What I got from the presentation is that you did a very systematic review of existing literature in trace clustering. I think this is very, very valuable and well done. The thing that I would like to ask is that if you look at the feature extraction part, then somehow that could be used for trace clustering, but could also be used for other things. So for example, if I think of the work of the general chair with the feature extraction package in PROM, and I also think about, for example, all the work that has been done on prediction, it always is about feature extraction. And I think that is more a comment. I feel that in this community, it would help if there would be standard software to somehow facilitate this feature extraction, because I think many of the things that you present would be reusable for other people that are not doing trace clustering, but are doing, for example, prediction. Did you think about this?
Exactly. Thank you, Bill, for your question and your insight. This is really valuable feedback for us. This is completely correct. With most of these building blocks are important for whatever we do later. So the reason that actually, which initiated this report, the motivation was that we looked into several possibilities, but everywhere we went, we just went to one step. We looked one step back, and we saw that the problems are laying into still process discovery. And solving problems from the very beginning, we understood that enhances the other, let's say, more sophisticated parts of process mining, no matter it's discovery, conformance, or prediction or enhancement. And therefore, we kind of focused on this part because we understood that these features are extremely important in the later parts. We also could think, for example, that feature generation could, maybe we could create a line directly from feature generation or feature selection to clustering or classification techniques, because they all use those features. This is extremely important, and the sooner that we solve these issues, the better results we get in every step of process mining, which we do later.
Yeah, so for example, this year at the conference, we see a lot of work on causality between different variables. And in all of these works, there has been a feature extraction phase somehow to talk about causality between different variables. And it's another purpose, but it's using the same things, I think.
Exactly.
Thank you.
Thanks a lot for your nice discussion. I want to thank all the speakers and also participants. I also want to thank the organizers of this wonderful conference, especially Massimiliano and the team in Padua. I hope to see you all next year in ICPM 2021 in Eindhoven, but this time, of course, in an in-person conference. Take care and stay safe.
Wait a sec.
Yeah,
so we are here. So we wanted to close the conference. So we want to thank all the participants, especially those that are arriving until the very last session at 10 past 5 on Friday. I'm glad that this time we still have more than 100 participants here, willing to still hear about process mining. So we hope that you enjoyed the conference. I think it was a good success. It was great. Industry Day, I was doing some computation like yesterday evening, and I think if I sum all the participants, all the sessions of Industry Day, we overtook 300 participants. So I think the success is clear here, and nothing would happen without the chairs, the participants, all the authors and speakers. So we want to thank all of you for this. I don't know, Alessandro, you want to add something? Or?
Yeah, of course, huge thanks goes to you that you were actually doing all the job. I mean, the operational details, managing everything, putting everything together from the real work was done by you. So this thanks to you. And it was unfortunate that it was not possible to organize a conference in presence, because we were also working a lot for the venue, for organizing everything, to have a venue that was large enough to host everybody. And but on the other side, it seems that this format, virtual format, at least for this conference, because other conferences I've been attending in virtual format were not so well attended, even if potentially they would have more participants than expected at this conference. So I think this shows that the community is really committed to this area, is really believing in the field, this growing field. So this also is a merit of Bill, of the task force that was started in 2009. Actually, we have also to thank the AAAI Computational Intelligence Society that was actually allowing the startup of the task force, and we are here thanks also to the idea that at that time was brought forward to start with the task force, and Will was of course the right person to start that and to create this so successful task force and area. So this is it. I mean, now Massimiliano can relax.
Yes.
After very intense work, especially the last month has been very, very heavy for him, and also for the team that is helping Massimiliano. He was learning a lot also about virtual conferences and Zoom and WOVA, and well, not everything was perfect, but it was really difficult. So you have to believe that it was not easy.
Yeah, thank you. And yeah, you see, I just want to show you again. There are still people here. You see the last. Say hello to everybody. So this is the last part of the team that remains until the end for the very last support. So I think that's it. Finally, we got to the end and everything worked well. I think I'll go and drink a few spritz now. I really need it.
And we hope to see everybody in presence in Eindhoven.
Yes, we should be all there. Okay, unless somebody wants to ask, say some other thing. Otherwise, we close here. And all of these sessions will be recorded. And now, little by little, we're putting all online, editing some sessions to remove some glitches at the beginning, the end. But we will inform you through UVA as soon as this is over, because the system will remain up and running for 6 months more. This is what they told me. So you will still be able to access all the material for the next 6 months. Nonetheless, the presentation, fortunately or unfortunately, this presentation will stay alive forever, as long as YouTube works, because they are all on YouTube. If once they decide YouTube is obsolete, then they will go away. Okay. And this concludes everything, and enjoy your weekend, and hope to see you soon in person. Eventually, this COVID will be gone.
Thank you.
Thank you
Well
so much.
said. Thank you very much.
Bye-bye.
Thank you.
Bye
very much.
bye.
Thank you. Bye.
Bye.
Ciao.
Ciao.